I'm interested in how to make a quantum computer work, like how to build it in real life. The way we try to approach it is to not make this transmon qubit, but make what we call cat qubits. These qubits are very interesting because they kind of intrinsically suppress part of the noise. And that allows ourselves to envision a full-scale, like fault-tolerant quantum computer with much less of these cat qubits than you would need of like regular.
So, second day of QIP Riga. Today we are a little bit tired, all of us. We have Christophe from Alice and Bob. Christophe, I'm super happy that you're here. Alice and Bob is a French startup,
Correct.
famously known for their cat logo. I assume from Schrödinger's cat.
Indeed. Yes.
So, and you are specifically reducing noise in quantum computers. And I'll give you the opportunity to introduce yourself.
Yeah.
What do you do at Alice and Bob, and what was your journey into the quantum field?
Okay. So so I'm Christophe Vuillot. I grew up in France, and I did some like computer science and physics studies into a PhD on quantum error correction, where I moved to Germany and then the Netherlands for my PhD. Worked with Barbara Terral there. And then came back to France and continued on working on error correction. And this is like, I'm interested in how to actually make a quantum computer work, like how to build it in real life. So that's why I really like this the topic of error correction, because it's really crucial in making these things. So yeah, since I went back to France, I got a researcher's position at INRIA, which is a research institute like applied math and computer science. And since a year, I've been working for Alice and Bob.
And how old is Alice and Bob? Is it?
Yeah, so it's like it was founded in 2020, I think. And yeah, and I joined a year ago to lead the QEC team there. And yeah, maybe the kind of the pitch of Alice and Bob is we're trying to build a quantum computer on like superconducting chips.
Do you produce them yourself?
So yeah, we build the whole thing. And the way we try to approach it is to not make like this transmon qubit or like similar qubit, but make what we call cat qubits. And yeah, the cat is for Schrödinger's cat.
Yeah.
So these qubits are very interesting because they kind of intrinsically suppress part of the noise. So the idea is that, what's a qubit? It's a system with two different distinguishable states, and that behaves quantumly, so they can be in superposition and things like this. Now, if you want to have quantum superposition, these states often needs to be on like very small physical system to be able to behave quantumly. And that was kind of the where this Schrödinger cat experiment, thought experiment comes from, which is, okay, if we believe quantum mechanics, it should be able to make superposition of objects that are like very big, like macroscopic objects. So say a cat. And that was the thought experiment. Like, can we believe quantum mechanics if it predicts that I should be able to put in superposition of dead and alive a cat? And physicists have been like fascinated by this kind of question, and some of the first experiments that demonstrated that were, I believe, like in optical systems, where people made superposition of states with many photons, and so they called them cat qubit states because they were kind of the first demonstration that you could put in superposition relatively
So you
large
didn't come up
systems.
with the cat qubit name, but it was already.
The name was there for
Okay.
for historical reason for a long time.
Yeah.
And then so what we do is that on our superconducting chip we have some like resonator, microwave resonator, and those behave like they can contain microwave photons, and basically we embed qubits into them by using these cat qubit states. And so when we do that, it's such that the two states of the qubit, the 0 and the 1, they are in a sense far apart because they are relatively large in number of photons. And because of that, there's very little so-called bit flip. So the state 0 very rarely turn into the state 1. So and that's kind of the intrinsic error protection that we try to harness with this cat qubit.
But do you want to reduce the errors to 0, or is it good that you have still some noise in the quantum?
So I mean, when you're trying to build a general fault-tolerant quantum computer, you want to reduce the errors to arbitrarily low, right? Now these systems, they can reduce one type of error, the bit flips, very very low. But now, because we want them to behave quantumly, they are in superposition, and now you can kind of have other type of error, so-called phase flips, and those the cat qubit, they don't protect against them. So what we need to do is just to use these like qubits which have very little bit flip but normal amount of phase flip, and we just have to deal with the phase flip when we build the quantum computer, basically. So that's the main idea. And so like maybe the terms for expert is biased noise qubits. So qubits with only one type, like mostly one type of errors, and that allows ourselves to like envision a full-scale like fault-tolerant quantum computer with much less of these cat qubits than you would need of like regular superconducting qubits.
And what convinced you, or what convinces you, that the standard approach of having software error correction, or let's say classical computers to error correct, isn't the right approach, or maybe not the right, but isn't the correct, but go more to the physics level of using cat qubits instead of qubits?
Yeah, I mean, so I wouldn't say that so we're using error correction just in a different way. So we really need as a quantum error correction theorist, I really believe in the need of error correction to reach fault-tolerant quantum computer. It's just that the most you use in your knowledge of your hardware in your quantum error correction, the more efficient you can be. So that's really what it's about. So with this superconducting system at Alice and Bob, we really have a deep expertise of how to control the system, how to engineer this cat qubit state, and this makes for a very efficient way of like suppressing one type of errors. And then on top of that, we need to like deploy the whole machinery of error correction with the remaining thing. But now our life is much more easier because these qubits are very noise biased. And so it's really about using in the best way possible your control of the hardware.
And what is an oscillator? Can you explain that?
Okay, an oscillator is like you pick a string, you put a mass onto it, and then you have it move, and that's an oscillator, right? So that's the classical pendulum is an oscillator. Now, this is, of course, we want somehow a quantum version of that. So I don't know if you've done some electronics course or something, if you put capacitance and inductance together, and then you put some current in it, then the current is going to oscillate. So now the oscillator lives in the electromagnetic field. And actually what's happening is like if you take this type of circuit and you make it very small and very cold, you will still have an oscillator, but now it's going to behave quantumly. So it's like, yeah, electromagnetic waves on the chip, and that, yeah, that analogous to just a pendulum.
And so do you see the error correction more on the physical side or on the software side?
I mean,
or is it the hand in hand? Should it work hand in hand?
Yeah, we do basically both, right? So you basically you have a physical system that is very messy, and you control part of it, and your goal is to extract the best qubit that you can out of it. And then, depending on how much noise left on this qubit, you do like maybe more what you would call software error correction. But it's I mean it's a whole, like during my thesis and during like even in my recent studies, I think a lot about this type of question. So like trying to tailor the error correction the closest possible to your physical system. Like let's say I don't have qubits, but I have qubits. I have like infinite dimensional system. Can I just design codes that are the best for like the physical system I have? And there's so the like the.
But do you need a new type of software then for CAD qubits in contrast to, let's say, general purpose platforms or the general scalable platforms like IBM?
I mean, you can. I mean, all of the tools they can be reused like right away, and then but you can try to also look for like spaces that have not been explored. So the like bosonic code in general have a lot of potential, and there's a lot of spaces that hasn't been explored in bosonic code. So that this is a place where we could find ways to just reduce the size of the computer, have some more efficient error correction.
And do you think that the philosophy of Alice and Bob to specialize highly on CAD qubits goes hand in hand with other companies who are trying to produce a quantum computer, or is it different?
Okay, I'm not exactly sure what you're referring to. I would say, I mean, we're trying to use the like the best of our expertise to build a computer.
Sorry to interrupt. What I want to say is it compatible, let's say, with the efforts of Google Quantum, or is it more a different path which is not compatible?
I think it's definitely compatible, right? If you just like it's very similar technologies, like superconducting circuits, very similar controls, like microwave controls. Now the precise way we use the chip, we use the control is different, and we try to get an edge in that. But definitely, like any tools they develop, they can be adapted, like reused, adapted. Any tools any techniques we develop can also sometimes be translated. I don't see it as a particularly like disjoint path. It's more a specific way of building the computer that we are good at.
Would you say the controllers are one of the main restrictions right now to scaling quantum computers, or advancing it, not scaling?
I mean, I think there's many places where there's a lot to do still. I mean, of course, controls needs to scale with the chip. So
I mean, the larger the chip gets, the more controls calculation you probably need to do, right?
Yeah, but I mean, sure, but a lot of it is like also, I mean, a lot of it is repeated, right? So so those are like problems to be solved one by one. There's a whole stack of a lot of problems. Some like very easy, some difficult, some just.
Out of the whole stack, that interests me a lot. Out of this whole stack, and you have a very good overview of the whole stack. where would you say is one of the biggest challenges the industry has to overcome or allocate more resources to, or what would you say is the general biggest signal of progress?
I think right now people are ready to get into the like so-called like fault-tolerant era. So just to get past the like really demonstrate clearly that you can run error correction, that it drives the logical error rate down, that you can do it routinely on bigger and bigger systems. And once this like error correction becomes routine, I would say that's really when we go to the next level of like squeezing more like bigger and bigger algorithm onto the machines. So for me, it's really making all these blocks necessary for error correction click with one another. That's the current like.
If I'm a PhD student right now, or want to jump, let's say, from software engineering of classical computations into the field of quantum, what is the most sought after field in error correction?
There's many aspects, I think, of error correction that are kind of current topics of development. So there's really the aspect of trying to find the limits of how many like how much more efficient you can make the code or the space-time codes, like how because this whole comes with a cost, right? You want to suppress errors, you need to use more qubits and do more operations to extract like a lower error on some logical, and this comes with a cost, and this cost is the like one of the main obstacle to get large computer. So like reducing this cost as much as possible is and understanding like the limits when have we reached like the best we could do is a hot topic, and then this is just about like so-called quantum memory, just trying to have a lot of very good qubits. But on top of that, you want to compute. So the kind of the other area is to find the best ways to do quantum logic on top of the error correction. So I think that these are like the main topics to be.
So if to summarize, it's still a problem in algorithms. Should I focus more on algorithm design to get better error correction, or?
So I find the term algorithm a bit confusing there because there's also like the algorithm that you would want to run on the quantum computer.
Yeah.
But here it's more about,
let's say, error correcting code.
Yeah, it's about the fault-tolerant protocol, right? So whatever you're doing on a machine, so that at the end of the day you can like simulate a quantum computer with less noise. So so all of this is like improving years after years. Still.
And how much classical computers do you use in your daily job, and how much of a stack of Alice and Bob is a classical computer?
I mean, there's a lot of my work is about simulating and predicting where we want to be. And then I mean, all the controls is like classical control electronics. There's this decoder problem where you have the syndrome, you need to figure out what happened during the computation. So this is also a classical decoding part. So there's a bunch of like classical compute helping the quantum computer next to it.
And do you have special access to a supercomputer, or are you using some traditional cloud services for this?
I mean, we have both. For different contexts. I mean, I don't have anything particularly interesting on this point.
Okay, no, I'm just asking. All right, so maybe how do we benchmark CAD qubits, and how do we evaluate them? Are they differently benchmarked or differently evaluated than normal qubits?
Yeah, I would say a little bit different because like usually normal qubits you can just talk about like to get a generic number, you can talk about the fidelity of the gate. So it's just like one number that tells you on average how good you are. This doesn't work so well for CAD qubit because it doesn't reflect this really useful property that the noise is biased. So usually for like CAD qubit, you want two numbers, right? You want basically how much bit flip and how much phase flip. And the kind of the difference between these two numbers is what we call the bias. And then this allows to understand like, okay, where are you at in terms of how to what's useful with CAD qubits.
So let's touch a bit on cryptography, since our company's main goal is to advocate for post-quantum secure cryptography, and everyone should ideally today be ready and use quantum secure encryption. Everyone should use quantum secure encryption, assuming that CAD qubits and Alice and Bob's approach and your work contribute towards a faster timeline of an error-corrected quantum computer, maybe a fault-tolerant quantum computer. How does this impact the timeline of running, let's say, Shor's algorithm or something on top of that?
Yeah.
Do we need less qubits than previously projected to break, let's say, RSA encryption?
So yes, indeed, we have a few works on that. So to really try to fully estimate, so do like a full resource estimation of what it will mean for us to run such an algorithm. So to like factor some relevant numbers. And basically, so I mean this kind of resource estimation, it's not so easy to do because there's a lot like you have to make a lot of assumption to get to the final numbers, but and assumption on like how well you will be with these large systems and everything. But like when we put maybe like our most optimistic numbers about like how far can we push the bias, things like this, like how well can we put the qubits together, we can get like significant reduction in the size of the machine. Like we can get up to something like 200 times smaller than like a similar machine that uses just transmon qubit, so like superconducting platforms. And so that's why we're pretty excited about our solution, right? So it's like we need to have like a finer way in how we control the qubits, but then we need much less to have like a useful
So 200 times larger in that sense means you need a 200 times smaller amount of qubits than previously assumed.
Yes.
So if the estimation previously was 1,000,000 qubits to run Shor's, you would need with an Alice and Bob supercomputer, you would need 1,000,000 through 200.
Yes, that's the type of computation that we can do.
And where are you? And where are we currently? With like what's the number right now, and what's the projection? Let's say 5 next year.
Yeah, so right now we are really working on this, like just demonstrating like building blocks of error correction with like a few, like in the tens of CAD qubits. And then, okay, I don't know the room by heart, but like we have some details up until like 2030 to slowly add complexity, like demonstrating like logical gates and then like magic set distillation, and then having like our like most efficient codes like to have as much logical qubit as we can. So yeah, okay. The precise numbers I would point you to our like roadmap, which is online on our website.
Of course.
Um,
But do you also see an acceleration from a potentially more optimized algorithm than Shor's?
Sure. I mean, when we first did the resource estimation, so there was basically so right the kind of the first Alice and Bob papers we have are like based on just cat qubit and a very simple repetition code, and already there we can like estimate some savings. And then there was some work from Google, for instance, where they did a detailed resource estimation for like surface code, like transmon-based platform where they were at 20 million physical qubits. And then we can have, I think, our first improvement of our like resource estimation are based on this type of compilation of the Shor's algorithm. And then since then it went down around like 1 million. So we have not publicly updated our numbers, but that, I mean, a lot of these techniques can be reapplied to what we have, so that reduce still our numbers. And then, I mean, this is something it keeps going down, right? And then we found out some more efficient codes. That's where we get to this 200. So this is still evolving. Like people are still hacking away at different places. So either like the algorithm itself, or the error correction,
So the timeline just keeps accelerating in a sense.
I think so, yeah. It's of course it's very difficult to be precise in this kind of things because you never know, like, yeah, when we'll run out of ideas to improve or things like this. But
and do you think that a big transition of cryptography from RSA to, I don't know, lattice-based encryption will come from the advancement of a quantum computer, or people realizing that, or will it be because organizations themselves want it? So is it either we are seeing this in let's say in this world, or are the boardrooms now becoming more alert?
I think a little bit the second your second point. So I mean, okay, I'm not an expert in post-quantum crypto. I just know, so there. I mean, people are aware of this potential problem down the line, and you can see things like the NIST competition for post-quantum algorithm that kind of already tries to establish some alternative, and they're doing it now because, I mean, it takes time for this kind of stuff. You need to find the replacement, and then you need to build confidence on them. You need to try to break them and everything. So I think people are already, like, nowadays thinking about this and thinking about transition.
And maybe to go back, maybe about your job and Alice and Bob in particular, there's a high level of uncertainty when you're working in quantum, since new findings can arrive tomorrow, but also potentially in 15 years or 50 years. How do you deal with that in your daily life, or is that something you are kind of used to? Like typically in companies you have, you know, revenues you hit or profits you make, and it's just, you know, that. But here in our space, it's a big preparation for the coming of quantum computers. And in your case, you are actually building the computer itself. But still, there is a lot of uncertainty.
Yeah.
And something you projected, which could take you maybe a year, can take you well over 3 years, or sometimes a month. So how do you deal with that?
Yeah, I would say, I mean, I really come from like a research, like academic setting. I think part of my job is still in this place, right? So we are exploring some scientific ideas and trying to, like, in parallel apply them in like our current setup, our current things that we're building. So for me, that's part of the of the task is like split between actual like research and then trying to apply it directly. So for me, it's really the same sort of uncertainty that comes with research.
And if you succeed in your job, how will the next few years look like? Where are we heading?
Okay, so I mean, we have a dense roadmap. We have a lot of
I mean,
things
let's say
to demonstrate.
let's say we meet again in 5 years. How does the world look like? Or 10 years?
Yeah.
Whatever you want to pick, rather. Let's say 10. Maybe it's easier.
So I think that's a difficult question. I think for me, there's like, as I was saying, like there's a lot of unanswered question in like how to best build error correcting codes. Like in particular in this, for instance, in this like larger space of bosonic codes where you don't only have qubits, but you also have like more complicated physical systems. So the like, and it's the same, like if you think about like classical computers that we have now, like year after year, they're not the same basically, right? So if you
always improve since I'm
alive.
yeah,
if you open them, it's like it's really it's improving still. So that's kind of the mindset I have.
But any applications you have in mind you would like to see on a quantum computer?
Particular applications?
You can also cover industries, whatever you like more.
Yeah. I don't know. I think it's kind of the physicist in me is really interested in all this like physics simulation, like many-body physics, trying to use this computer as a tool to understand this type of things. I think it would be very interesting.
All right, and are we still constrained, from your opinion, in the private sector by the academic sector, or is it more that the academic sector is restrained by the private sector because the private sector cannot provide hardware fast enough?
I don't know. I think it's still like at least the interaction we have between Alice and Bob and like our academic partner are very like very dense, very fruitful. It's a really, for me, it's a really positive interaction in both directions. So I don't see any conflict like this right now. At least in our setting, it's a very nice.
And from your personal opinion, if we solve a quantum computer, or more so open questions, how to combine quantum and relativity, maybe gravity, is there some new frontier already you're thinking about? What comes after that? Like, what would be the next question to solve? Like the next big field.
So what question will?
Like let's assume we have exactly. So
Yeah.
let's assume we have this now. But do you think we will end up in a state as humanity or as researchers where we're like, okay, now we have the final answer, or will this bring up new questions? And what these new questions would likely be?
My personal feeling is like I don't really see like the end of like questions that we could ask. So I would say I more see a way to use this tool to ask more questions about materials. So
And do you have something in particular in mind? It could also be from science fiction or something you are personally interested in.
No, I don't think I have something terribly specific. No. Yeah, sorry.
All right. Cool. Yeah, sure. You want to sit here?
So my first question is thinking back to the history of classical computers, how we started with single-purpose circuits, all the way up to completely programmable computers. Does it make sense that quantum computing might follow the same trajectory, or do you think it will stick with very specific single-purpose problem solving?
Yeah. For me, it would make sense if the similar path happens for quantum computers. So of course, it's like and it will be, I think, at first constrained by the size of the machines, right? So the first machines that useful that we'll have will still be like pretty small, and we have to really pack the most useful algorithm we can on them, and that's where I think like special purpose computers or special purpose architecture would really help, because if you really optimize for certain algorithm, you can basically be more efficient with the size of the machine you have. But then as we progress, and maybe it's easier and easier to make bigger and bigger machines, like if you can add some flexibility in your programming, like this will happen. So I could very much see the same thing happening.
Okay. So on that, when we unlock general programmability for classical computing, we ended up creating all of these like digitally native products, so like instant messaging, like encryption schemes, things like that. Are there any completely quantum native applications that like researchers have been talking about that just is completely unfeasible on classical architecture?
So I'm not exactly sure. I think that, so I'm not such an expert in the zoo of existing quantum algorithm, but I think some classically difficult tasks have some interesting quantum algorithm. Things about sometimes decentralized protocols have some quantum version that are maybe more efficient. There's this whole topic of quantum money, where you use like a quantum cryptographic protocol to certify someone. So it could be that, yeah, really having very large, robust quantum computers, and maybe like some also small networking between them would enable this kind of application that we don't have right now.
Okay. Last question, if you haven't answered it already, is what's the main bottleneck that Alice and Bob found with so like the current pipeline we've got, where we have like quantum computers which try and like encode structure of a problem and using classical computers to verify versus like building a bespoke architecture for what a qubit should look like. What's the bottleneck you found with the former that led to you thinking the latter is a good solution to put on top of it?
Okay, I'm not exactly sure to fully understand the question. I think we really, started from this expertise in this type of qubits, and seeing that we could push it and leverage it so that we might end up with like very efficient quantum computers, and that's what we're pushing.
Okay. Cool. Thanks for coming, Christophe. It was really insightful hearing your views, and hope we can see you again.
Thank you.